And it kind of looks like it's intimidating. You have to do all these things. You got 5 lines of instructions. But really, when you start doing these sketches, you do the same thing every time. You put the 2 beakers with the salt bridge in between, the 2 electrodes with a wire, and then just make sure that you do everything that it asks you to do. Show the direction of electron flow to the wire. Show what is happening with the salt bridge. I haven't talked about that. I'll talk about that with the answer to this one too. Now in this case, what does it say? What does it say?
Overall balance.
This cell needs to be based on these 2 half reactions. If you look at these 2 half reactions, they're both reductions. Can you have 2 reductions working together?
No.
No. It's got to be one as an oxidation and the other one as a reduction. So that means one of these has to be turned around. You determine which one gets turned around.
I'll choose the easier one. Oh, they both have the same amount.
Spontaneous.
Yeah, wait, once you want to make it smart and then before you make it spontaneous.
Oh yeah, you flip the first one, so
Yeah.
it's still, yeah.
You need a positive cell potential for it to be a spontaneous reaction.
But that's not true.
In the way that we're going to draw the equation.
On the test, I know they're going to do some questions.
So go ahead, figure out what the overall balance. We do need it says give the overall balanced equation. So in this case, you do need to balance the equation. Notice the half reactions are balanced already. But when you put them together, the electrons need to cancel out.
Oh my god, we have to multiply by 2.5?
No, well, I guess you could. Or you can multiply 1 by 5 and 1 by 2. Per iodic, not periodic.
Show any person that word, they'll pronounce it clearly.
I know they will.
Even you, if you didn't like, you're probably sure.
So let's say for instance that
I
that would give you negative 0.1.
Now, if you're watching this from YouTube, this is a very slow process because my intention is to show the question, have everybody try to work it out on their own. That's why we're waiting so long. Not like it's a long time. This is.
Can you just do it?
No.
Yeah, I can do it.
Oh.
Can you just do it?
Oh,
Yeah, Rose did.
shut up, Samir. This is why everyone gets mad.
I know, but at least Mr. Moore's happy about doing it.
Yeah, I'm very happy about that. Not just saying we can just do it, so I can play with my phone.
Okay, I give up.
Yes.
Multiplying is
Why are you having such a big deal? What is your problem?
Don't be a spoiler.
much time do we have? 5 minutes?
How much time do you need?
This takes me.
That's all right. I don't want to rush you.
How do you figure out what's the anode?
Well, they're both written as reductions, so you know the one of them needs to be turned around. You have decided which one gets turned around, right? Which one? Okay, so now the top one is an oxidation. That's what you put into the anode. The anode is always the thing that oxidizes.
Oh, yeah. Wait. Wait, when you say switch it, we switch the whole equation?
That whole top half reaction gets turned around. And then its potential becomes negative.
Wait, but then Mn plus 2 goes to MnO4. Right?
Yes, which is weird.
Isn't that?
But because the IO4 has a higher reduction potential when they work together, it is spontaneous. Right. You don't have to label the water. Hydroxide, what do you do with the hydroxide?
It's going so hard.
Are you stumped on something? What are you stumped on?
Or, like, what's the 2 electrodes are?
Okay, so in the oxidation, that top reaction, you got ions making ions. What metal do you use? Always use PT if you have an ion making an ion. And then what about in the second half reaction? Again, it's ions making ions.
Oh,
So you have a platinum electrode in both.
Oh, that makes sense.
And that's totally fine.
I know I've been confused. I've been looking at the diagram of the last problem, and then looking back at my work, and getting very confused. I was like, I remember fixing this one.
Oh man.
Oh, I think I got it. Oh yeah. If you write the Y notation, it doesn't make sense then. Mn plus 2 goes to Mn.
Yeah, so you have to put the Mn plus 2 first. After the platinum, you gotta go platinum and then Mn plus 2.
Oh, electrodes go first.
Always. And in the cathode, they go last.
Yeah.
Yeah, then you can reduce it. You can drop both sides by 5. Oh yeah, that's what you do with the hydrogen.
Yeah, I'm not letting you off on this one. I can do this.
Oh my god.
Okay, in the anode, what did you decide is oxidizing? You took that and made it negative. I think this is the oxidation. Because that's getting off right. So that half reaction goes in there. So you put everything that's not water. So Mn+2 goes in there, MnO4 goes in there. You don't have to put any numbers there, just those three substances. Into the same thing.
Working on the line notation, so does the cathode go from IO4 minus to IO3 minus?
Yeah, but you need a hydrogen in there too.
And the MnO4 minus too.
Both of them need hydrogen. Yeah.
Do we put the actual amount of this one H?
Yeah, you don't have to balance the line notation at all. No numbers at all in those.
I don't know how this is harder, easier.
Okay, shall we go over it?
Sure. See how bad
Yes, please.
That was a tough one. How do you know whether to put IO4 minus or IO3 minus? Are you putting the thing that gets
Where?
the solution? The cathode is IO4 minus.
Yeah. And in the cathode, the IO3 belongs there too. It should be in the beaker. Put the products and the reactants.
Everything's in the beaker?
Yes.
That beaker is
Everything except water. You don't have to put any, I mean the whole environment is water, so you don't, any water that's produced by a half reaction, you don't have to include that and red assemble for it. But this is what it looks like. Both sides have a platinum electrode.
That line notation is going to be so big.
Yeah, I forgot to do the line notation on this, so I'll do that in a moment. But yeah, over here we have Mn+2, an ion, releasing some of its electrons and becoming MnO4. The electrons leave and they go over here. And here the per iodate, IO4, goes over there and takes the electrons and makes IO3.
Where's the Mn then?
Right there.
Oh.
It's in the cathode. It was oxidized.
Why is H plus in both?
Because both half reactions had H plus in them.
Bro, some of it gets canceled.
When you turn that around, H plus was a product, but you include both the reactants and the products.
Wouldn't they get canceled out?
No. In the overall equation, they don't even cancel out.
Yeah, well, like it goes right then. There's only 6 substances.
Yes. But since that half reaction is not touching that half reaction, you need the hydrogen in both.
Oh, is it because the salt bridge?
Yeah. I mean, not because of the salt bridge, but
Like
they're
the H
connected
plus-
by the salt bridge, but both of these processes either need or give off hydrogen, so you need to include the hydrogen in both.
I was really close.
Were you?
That was actually close too.
I didn't add the H plus.
Oh, that was great. Yeah, but you do. You need the H plus. The only thing you don't include in your sketch is the water molecule, because you can see this line. This line represents it's all a solution in water, so you don't have to say that it produced water or took in water. That's just understood.
Wait, so can you explain the H plus again one more time? Why
Yeah,
is it-
because over here, for the oxidation, it was the oxidation that you didn't want it in, right? The anode?
Yeah, I flipped the.
So this top one gets flipped around.
Yeah.
The Mn+2 is a reactant, and then it loses some of its electrons, and produced are permanganate and hydrogen ions.
Yeah.
The hydrogen needs to be there.
Okay.
And then in the cathode, this will not reduce unless it has hydrogen ion. So the hydrogen needs to be in that one too. So in the sketch, you treat the anode and cathode as if they're separate reactions. They're half reactions. But yeah, just because hydrogen only shows up in the overall equation on one side, doesn't mean that you don't need it on both of those. If this process needs hydrogen or makes hydrogen, you include it. Same thing over there. Jess?
Because.
Because this, we start with an ion and make an ion, so we use platinum. Over here, we start with an ion and make an ion. So that side uses platinum too. The only time you use a non-platinum bar is when you have like if there's a metal as a reactant or a product in your half reaction. Like in this example, iron was reacting. One of the reactants is iron. So you use an iron bar, not a platinum bar. Yeah.
When we needed H plus ions, do we add like a strong acid or something?
Yeah, that's what that means. H plus means we would have to add strong acid to both of them. Yep. No, no. You can have acidified permanganate. It's perfectly fine. It doesn't react with the permanganate. It just makes the environment acidic. So you got the hydrogen ions that can bond with the oxygen when the oxygen leaves. Yep. And the same thing over here. Acidifying that doesn't cause these two to react differently. Okay, now I didn't show the line notation. We need to do that. I know some of you were a little bit unsure about the line notation. In the anode, the electrode is platinum, so we'll put that there. Everything else is dissolved, so I'll make the line. The reactant is Mn plus 2. And that's going to make hydrogen ion and the MnO4. This is our anode. MnO4 is the product. And hydrogen ions are the product. No, don't be intimidated by that. Look, when we turn this thing around, manganese makes MnO4 and hydrogen ions.
I thought you have to split up the Mn plus 2 and the MnO4 line.
You do?
Oh, wait.
What do you mean split them up?
Wait, look at mine. I don't know if this is bad. I just forgot.
Yeah, but because they're both aqueous, you put commas in between them, not a line. The line separates physical states. Since they're both the same physical state, use commas. Yeah, if you're watching on YouTube, the question was, how come we don't put a line in between those? And it would be wrong to put a line, because the lines are there strictly to separate different physical states. Since these are all the same physical state, you don't use lines, you use the commas to separate. Okay, so this is our entire anode, and then we have the separation between the anode and the cathode. Over here, our last thing is going to be platinum, because that's the electrode. What's reacting is the IO4, and all these are aqueous too, so we're only going to have one single line over here. IO4 is going to make hydrogen ion. Actually, it's going to use hydrogen ion to make IO3. So with 3 examples today, hopefully you can at least start to get the feel for how to do these, how to sketch the cells, come up with a balanced equation, write the line notation, all that stuff. Lots of practice in the exercises. You won't be disappointed. Just one other thing today, very quickly, the battery lab. For the battery lab, that happens a week from tomorrow, on Wednesday the 18th. Tomorrow's the 11th, so yeah, Wednesday the 18th. You need to bring in your chemicals from home. Something has to oxidize and something has to reduce. You want to try to have the highest voltage possible.
What do you recommend?
Where do you get chemicals?
He's not gonna
I have nothing. I can't even tell you where to get stuff. Not that I can't, I won't. I just want you to come up with stuff on your own.
This is the case.
You might ask other teachers. You might ask people that you know, mom, dad, uncles, aunts, whatever,
Can we ask Mr.
friends. Mr. Hebel won't say anything either. Some people are sciencey and they'll know where to find stuff. Like if you go up to somebody and say, hey, I need hydrogen peroxide, but it can't be more than 10%. They might know where to find it. And you can stay in Troy and find 10%, a bottle of 10% hydrogen peroxide right here in your little town.
We should buy up all the supply and sell it for elevated price.
So I'm not telling you where or what industry, but it's out there.
Kind of black market for the last day.
Let me have your attention, please. So yeah, I've been talking about the banned substances. These are for your protection, and you're going to think, I don't need to be protected. Yes, you do. Because you're high school kids.
Wait, I have a question.
I've had people walk in with a gallon jug of sulfuric acid, concentrated sulfuric acid. That's 18 molar sulfuric acid. It happened last year. And I was a little bit peeved at the student because this is a person that really knew what they were doing. They were a great chemistry student, and then they did that. And of course, it spilled, and it was a big spill. So now I have, if you try to clean up 18 molar sulfuric acid with paper towel, it dissolves the paper towel.
Really?
Yes. And then what is between your hand and the acid? Nothing. So we do have some absorbent material like cat litter that we use. It was a huge cleanup, big effort. I was very annoyed. Normally, we've been together for 3/4 of a year.
You use it, but then you spilled it?
No, I didn't want. I told them it was banned, and they still brought it. So they were marked down for that.
Oh.
Yeah.
So if it's a banned substance, like those things, so like.
Yes, you're going to be marked down,
What if it had like a,
and you can't use it anyway. So you're going to be marked down, and you can't use it. That's just dumb. Okay, you got marked down for just saying that. Yeah, I will have some, probably 6 molar sulfuric acid. If you need anything acidified, like you saw, if you wanted to do this reaction, you'd need hydrogen ions. I don't want you bringing in acids from a store or whatever. I'll have acid for you. That's the only chemical I'm providing. Okay? So, yeah, count on us having that. Now, when I say no group 1 metals and no halogens, I mean the neutral form of those elements. I don't want you to bring in neutral sodium. That's very dangerous. Neutral lithium, very dangerous. My first year of doing this lab, I had a really fun group of students. They were sharp, they were good. And they asked, I didn't know much because I was just starting to teach the class. They said, can we bring in a lithium-ion battery and take it apart? I thought, well, if you're going to take it apart, that's not the battery itself, okay. So they did. It was very funny. Nobody got hurt. But they had they unrolled a lithium-ion battery, which is a rechargeable battery, and took the lithium out of it. It was nice, shiny, silvery lithium, and attached it. And when a student, they were using a grapefruit to run this thing. You can do a little research. You can find that you can run you use grapefruit as a salt bridge. They stuck the lithium into the grapefruit, and it's sparking and popping, and there's stuff it's going. We're all wearing our safety goggles because and we're getting sparks and everything. It was really funny. So of course they got an extremely high voltage. They won, and they had gloves on too. So they were doing everything that they should do. I am not at all comfortable now seeing students handling that stuff. I knew that anything that could possibly go wrong would not be good. Somebody could get seriously hurt. So at that time I thought, we're not doing that ever again. It was cool, but we're not doing it again. So yeah, that has made the banned substance list. Halogens, some of your reactions will actually make chlorine gas. We need to avoid that, like bleach and acid. I've had students that have combined bleach and acid and make chlorine gas. Chlorine is a yellow gas. If you see a yellow cloud coming up, you need to undo it. Dump it out, and you probably have to evacuate, get away from it. You do not want to breathe